welcome back. Welcome back to Think Tech Talks here on a given Monday in the SOEST hour, and that's S-O-E-S-T. There's probably a song, we could put that to music. The School of Ocean and Earth Science and Technology at UH Manoa. I'm going to write some music for that. And we have Garrett Ito, but Apuzin Ito, who's a professor there. And I guess it's not SOEST so much as it's geology and geophysics at SOEST.
That's right.
Okay, and we have Greg Ravizza, who's an associate professor also in geology and geophysics at SOEST UH Manoa. And we're delighted to have them as part of the SOEST show. We're going to call this the introduction to the professional master's degree in science, which is called MGEO. By the end of the show, you're going to know a lot about geophysics and MGEO, which we'll tell you about later. Also remember that after the show is over, we have Kali'i Ehana Kako. Let's work together, and always interested in hearing what his guests have to say. Okay, so the first thing is, I don't feel I've done anything near to justice to describe and introduce you guys, so maybe you could help me out. Garrett, tell us about yourself.
Well, as Jay said, I'm a professor in the Department of Geology and Geophysics. My specialty is geophysics. And geophysics is basically the application of physical methods and, in many cases, remote sensing to detect and understand the structure of the Earth. And that's what I work on. I'm especially interested in the structure and formation of ocean islands. And being here in Hawaii is a wonderful place to conduct that research. And we've done some recent research in the Hawaiian Islands.
So, the creation of islands, do you think, and this is a really important question for me anyway, do you think that as time goes by, maybe in our lifetimes measurably, there'll be more of that?
It's happening right now, that's right. So many people are aware of Lauihi, which is a seamount just southwest of the Big Island, southwest of Kilauea, southeast I should say. And that's an island that's forming geologically before our eyes. So it's an active volcano, and it's growing very slowly on human time scales, but at some point, perhaps several tens to hundreds of thousands of years from now, it will surface.
How close are you to climate change?
My research is it's pretty indirectly related to climate change. Some people in my field are interested in, for example, sea level rise relative to ocean islands or relative to land masses.
Oh yeah, sure.
And there is an interaction between sea level rise and how the Earth responds to changes in sea level. I don't work on that myself.
All these things, it's like, I wonder, maybe you could answer this too for me. 50 years ago, were we studying this? Or was it, something that had not occurred to us yet?
Climate change?
No, geology.
Oh, yeah.
Was it geology and geophysics?
Geology and geophysics. Yeah, geology is a fairly old discipline, right? We were
19th century.
Early, or even before, 1800s.
Yeah.
Sure. We were, it's actually even before that. But sort of the modern technology certainly has made a lot of understanding available to us, for sure, in the last
Why do we
century.
need to know about it?
Well, I need to know about it because I'm fascinated by it, right? So when I go to the Big Island and see this incredible mountain before that encompasses the whole horizon, I'm fascinated of why it's there and what that is telling us about some incredible processes deep in the Earth.
Wow.
Certainly, and many people are interested because they live on these islands and they want to know why, for example, why it's here and what processes affect changes on the islands,
Let me ask you
including climate change.
The Earth is changing.
You bet, yeah.
And we're more sensitive to that now than we ever were.
Yep, that's right.
And we need you guys to tell us what's the next change.
Yeah.
Okay, Greg, tell us what you're doing at SOEST.
Yeah, so I'm an associate professor in the same department, geology and geophysics, and my interests are in isotope geochemistry.
What kind?
Isotope geochemistry.
Okay, that sounds like radioactive.
It is. We have actually tremendous strength in that broad area. Specifically, I am working on dating rocks, determining their absolute age in millions of years.
Are they nice when you go out? Do you drive
You know,
them to the movie?
they are very uncommunicative. I'm always trying to get them to tell me just simple things. How old are you? But in fact, I need to go into the laboratory, work very hard to tease out that kind of information. But at least
flowers.
Yeah, I don't know. That doesn't work. That doesn't work for me. But at least I'm better looking than the things I date. At least I like to think so.
We didn't rehearse this or anything, but you must get that question all the time.
I get teased about that kind of thing a lot, so I am used to it.
Okay, well, tell me a little about the relationship of the geology and geophysics. Is that a school, a department, a
It is the
division?
Department of Geology and Geophysics, and I mean, in essence, we are Earth scientists. We study the Earth in all its aspects. So, if you are interested in the environment around you, how it came to be the way it is, and if you're interested in the resources that we extract from it to run our societies, and how long they might last, all of those factors are tied into earth science. And so each of us, I kind of think of us as like a scientific equivalent of a food court. The individual faculty run research programs like a concession under the G&G umbrella, which is part of the SOAS, the School of Ocean, Earth Science and Technology. And we're passionate about the specific research questions that we address. And some of our passions are very scholarly in their nature. I'm fascinated by extinction events. And what may have caused them, which is a difficult thing to tease out of the rock record because they're so uncommunicative. But time is critically important in that effort because to understand an extinction event, you need to know whether the dying of all these species or genus occurred over a brief period of time, perhaps a year, perhaps a decade, or if it was a protracted event that took several 100,000 years. And answering simple questions like that is a real challenge for us.
Well, let's talk a little about your research. I'd like to know from both of you about that. Why don't you go first, Greg? And we have some pictures. Maybe we could.
I don't have any pictures for you. I'd be showing you
Garrett
graphs
has
and plots.
Okay.
Yeah,
Well,
yeah.
why don't you talk about your research for a
Sure.
minute?
I mean, I'll tell you what I am most interested in at this particular moment, which is something different than I've done most of my work on lately. I'm going back to the work I did for my PhD, which was actually studying the Bakken Shale. And you may know about the Bakken from an interest in energy. That's one of the major tight oil resources that's being exploited in North Dakota. So you hear about these big economic booms in North Dakota.
Very recent. This is
Yes,
a
very
relatively
recent.
new discovery.
In fact, when I was in graduate school, I finished in 1990, we knew...
What school was it?
Yale. We knew that the Bakken Shale was so full of oil that it was fracturing itself.
I'd like to know more about how they do that.
Basically, you cook something, and its volume increases because you generate liquid hydrocarbons. It overpressures and causes small little fractures. But these fractures never reached anywhere where that oil could leak out into a porous and permeable reservoir where it could be pumped. And so these radical people who are by and large not highly trained geologists developed the technology to go in and fracture these rocks and extract these vast amounts of energy. However, because I was doing my dissertation on this stuff, I've recently started to work with some of the oil companies.
Geology equals oil companies, right? I mean,
You know,
guys
it is
are married
very
at the hip somehow.
well. It's very interesting. I would say there's a broad schism between the academic community that is primarily concerned about climate change and the community of geologists who are applied and oriented toward extracting fossil fuel resources.
Or actually working for oil companies.
And who have a very hard time confronting the problem of climate change. And certainly,
Isn't that interesting?
at a corporate level, they are incentivized not to do so.
Sure.
Right. So,
Sure. So you'd rather be, both you guys would rather be in academia on this from a philosophical
so
point
this
of view.
is a great. I could take the whole show talking about this stuff, but I'll just tell
I'm
you.
glad we hit this.
I'll just tell you very briefly. So, during times in Earth history, when there is deposition of these very organic rich rocks that turn into the source rocks for petroleum, in many instances when there's a lot of this stuff accumulating, it seems to be unusually warm. So you're removing carbon from the atmosphere to deposit all this sedimentary organic carbon, okay? And so the time intervals when these organic rich shales are accumulating that are now being targeted for direct production of oil and gas, when they drill those drill cores out, they are like history books of what was going on in the environment at that time. So if you're interested in how the Earth works and what might happen on the Earth when it gets really unusually warm, these are exactly the rock records you want to look at.
Where does volcanology fit in all of this?
Very simply, there's a guy from the University of Rhode Island. He has passed away. His name is Roger Larson, and he had this, I would say, a transformative idea, and it was based on empirical observations that during times of massive basaltic volcanism, the ocean becomes less well oxygenated. There's less oxygen in the ocean, and these events called ocean anoxic events seem to occur where you deposit tremendous amount of sedimentary organic matter. And subsequent work has shown these episodes also tend to be warm. Exactly the processes responsible for this are not well understood, but they're intensely studied.
You know, your excitement is viral.
I mean, I love it. I love it. I consider myself to be tremendously fortunate to be able to work on what I work on.
But, you know, give me an example of something that would really get you excited in terms of finding something in geology and geophysics that would make you sort of dance around the block. What would it be?
You know, this is the disconnect. I think this is what makes, one of the things that makes it very difficult to be a good educator. This morning I was super excited because I was getting my first results from a sample that we had irradiated at a nuclear reactor at the University of Missouri that is I'm hoping will become a new tool for dating rocks. And so I was very excited to find the ratio of two isotopes of osmium-192 to osmium-186 has increased by a factor of 2 as a result of this irradiation. And that was very exciting to me. Now, it wouldn't be exciting to anybody else unless they had had probably a couple years of isotope geochemistry.
Garrett is excited.
No, he's not excited. Trust me. What Garrett and I do are worlds away, and he can appreciate the potential significance of this stuff if it works. But when you're developing new techniques, it's the nitty-gritty. It's positive results at the incremental level that you have to get excited about.
That last millimeter.
Yeah. Well, it's not even the last millimeter. It is sort of, these are the data we have that allow me to go and say, this is something that might work, and it's worth investing more effort on. But really, it's the matter of looking at a number that is 0.03944 plus or minus 0.0014 and saying that number is 50% higher than it was before I irradiated.
And now I can date rocks a lot faster.
Now I can try to improve the precision with which I can date rocks, and potentially do it much faster. Yes. But it's not like it's the finished product. It is an incremental step toward proof of concept.
Okay, we got 1 minute before the break.
Okay.
Tell me how this helps you date rocks.
When you date rocks, there is a radioactive parent that decays to a radioactive daughter. And so normally when you do analyses, you have to measure both the amount of the parent isotope and the amount of the daughter isotope. By irradiating these samples, I can change the elements. It's like lead into gold, but for me it's rhenium into osmium. You can change the rhenium into osmium and do a single analysis, a single isotopic analysis of osmium to get a date, instead of having to measure rhenium and osmium separately. And this opens up a whole variety of recipes that we might try to get more accurate and more precise dates.
Do you ever have to get permission from the parent?
No, but I have to get permission from the university to handle radioactive material, and I'm in the process of trying to do that. So one thing that happened as a result of this is I thought that these samples would not be very radioactive. I was leaving Missouri, and lo and behold, they were radioactive. And so I was able to take one sample that was okay. It had no radioactivity, but I left a whole batch behind. I cannot receive shipment until the good people who take care of the environmental health and safety and specifically manage our isotopes, our radioactive isotopes, say, okay, Ravizza, do you have a plan for handling these things? Are you going to be doing it safely? Are you going to need badges? And so I'm in the process of requesting that.
Oh, that's so exciting. And what exactly did TSA say? Do they have any interesting comments as you were boarding the plane with the radioactive?
No, but it wasn't. They have walk-through, they call them portals, that are extremely sensitive at the reactor. And TSA's equipment is much less sensitive than that. So
shows you.
Yeah, and one thing that few people know is when you fly across the continent, you get about the equivalent of 1/20th of an X-ray, just in radiation, because you're up higher in the atmosphere.
Ooh.
And so the amount of radiation that I had was completely undetectable using the very sensitive stuff that they had. I had to leave most of what I wanted to take home there, though.
Okay, that's Greg Ravizza, Associate Professor at Geology and Geophysics at SOWEST. And also we have Garrett Apuzan-Ito. Thank you. Garrett Apuzan-Ito, Professor at Geology and Geophysics at SOWEST. We're going to take a short break right now, and we're going to come back and ask Garrett about his research. You know, what I love about this show is we want our scientists to talk in their own vernacular. Talk science. Make believe we're all your peers and colleagues, and we understand everything, no matter how much we understand.
That's what we do anyway, science, right.
We'll be right back after the short break.
Aloha, I'm Nicole Horry for ThinkTech. For nearly half a century, the Hawaii Foreign Trade Zone No. 9 has brought the benefits of the Foreign Trade Zone program to Hawaii businesses and entrepreneurs. DBET, the Department of Business, Economic Development, and Tourism, operates Hawaii's Foreign Trade Zone program to encourage international business and economic development. The Foreign Trade Zone's mission is to increase the amount of international trading activity in Hawaii, thereby providing employment opportunities for the residents of our island state. For more information, see ftz9.org. I'm Nicole Horry. Mahalo.
Okay, we're back. We're live. We're here on Think Tech Talks. We're doing the SOWEST Hour, the School of Ocean and Earth Science and Technology, and we're talking about an introduction to the professional master's degree in science called the MGEO. We haven't gotten to that yet, but we're working up to it with Garrett Apuzan-Ito, professor at SOWEST, and Greg Ravizza, an associate professor at SOWEST, and we're having such a good time learning about this science. So, Garrett, tell us about your science. This time we do have some photographs, yeah?
Yes, we do. Yeah, right. So my research is a bit different from Greg's, and I guess I'm interested on the physical processes that occur on the Earth at a variety of length scales. Everything from the size of the whole mantle, which is the sort of hot, sort of ductile layer of the Earth.
Starts 200 miles down. Is that right?
Well, yeah, that's in many places it starts 200 miles down. That's right. But it it continues all the way to the core, so the liquid outer core, and this is where a lot of the action occurs for the heat loss of the Earth. And so my interest is in the basically the tectonic processes and magmatic processes heavily related to the oceans. And so some of my research goes into studying the where oceanic crust is accreted at mid-ocean ridges. Those are very magmatic and tectonically active settings, as well as the formation of ocean islands. So that's another major way in which the Earth loses heat other than mid-ocean ridges.
So what are your techniques to measure?
Okay, so I use a variety of techniques. One emphasis is in theory. So I use a lot of numerical simulations related to convection of the Earth's mantle, also the dynamics or the deformation mechanisms of the sort of solid outer shell that makes up the tectonic plates. And I'm interested in the processes by which this heat is transferred to the surface and by which the plates accommodate that either by extension at mid-ocean ridges or at ocean islands.
So you're mapping everything.
Well, that part is basically taking observations and seeing, sort of looking with numerical models to simulate the processes that can explain observations and help us understand them. So the other aspect is more observational. So a lot of my own research has been in mapping areas I collaborate with geochemists who study the composition of rocks. I also collaborate with seismologists who use seismic methods to image the deep interior.
It's pretty exotic.
I
mean, the whole state of Hawaii, there
you know,
probably
it's just
can't be too many
just what
people
we
who
do.
know about this. You know?
That's right. It's maybe not a lot of people do that, but certainly seismic methods are widely used in industry, and it's sort of flourishing and solid with geophysics. That's right. So the seismic methods are our way of doing tomographic or CAT scans, if you will, of the deep Earth. That's right.
Okay, so why do we care?
Well, we care about this because we're interested in what processes affect the surface of the Earth. Volcanic processes are important, certainly to people living on islands, for example. The deep Earth is responsible for the motion of the plates and that affect earthquake. That's what drives the earthquakes.
You predict them?
Prediction is a very difficult issue.
It wasn't an easy question.
That's right. It's we're working towards being able to assess risk. Let's put it that way. Which areas are more prone to breaking and earthquakes? Where the large earthquakes are more likely to occur, that sort of thing. And there's also the hazards related to volcanoes. That's right.
So show us some pictures. We have 3 pictures that we took out of your website.
Yeah, sure.
And here's the first one. What is this?
So this is a map of Kauai. It's in the top of the picture, and the Niihau's to the left. And the color you see is an image of underwater topography. We call that bathymetry. And the target we were most interested in was the southern swell, if you will, just south of Kauai. Mike Garcia, my colleague, who's a Hawaiian volcanologist, and I led a seagoing expedition to survey this bathymetric swell. We wanted to know what it was. Some of the hypotheses we wanted to test, well, one was that it was some form of rejuvenated volcanism, such as it would be a massive form of rejuvenated volcanism, for example. And one smaller example is the Diamond Head volcano. Another hypothesis we were interested in is whether it was a massive landslide. So some of your viewers may know that there have been several huge island sector collapses into the ocean, such as the one off of Nu'uanu. It took roughly a third of the volcano well offshore, and we were wondering if this could have happened south of Kauai. And the last hypothesis we were interested in is whether it was in fact a separate volcano in itself, a low relief shield volcano that did not quite reach the surface and did not quite form an island.
So if we were going to have another Nu'uanu slide, where a good part of the island slides into the ocean out there by 10, 20, 50 miles, whatever it is, the way that happened, would you give us some advance?
You would want to know. I mean, that'd be very bad. The
I live in Nu'uanu, by the way.
Okay, well, you're probably safe in Nu'uanu because it's already happened there.
Okay.
But yeah, I mean, this is certainly a geologically dramatic event. There was probably a very large earthquake and a large tsunami. Fortunately for us, they're very, very rare. So geologically, they occur over geologic timescales. So it's the risk is considered to be very low. And there's really, well, we don't know a lot of why or when they occur, and this is part of the research that we're doing.
Okay, how about photo number 2? By the way, we're on Twitter, and if anybody wants to, send us a tweet, ask a question, make a comment about the science here at SOWEST, it's on the screen. It's at ThinkTech High. So send us a tweet, and we'll be able to catch it here and include you in the show if that's what you like. Okay.
Yeah, so this is an image produced by Ashton Flinders. He's a former master's student of mine, and he did this work this past year, actually, what you're seeing is a sort of a 3D perspective view of the Big Island. So the gray area or the brownish area is the surface of Big Island. And most of the colors, the green and the yellows, are colors that tell you the strength, the actual strength of gravity, the gravitational pull over the Big Island. And so we geophysicists use very sensitive tools to measure very small fluctuations in this pull of gravity to understand density variations and thus internal structure to the volcano.
You have to bury them in the earth?
The gravimeters?
Yes.
No, this is something that's a handheld instrument, typically, in this case, on land, and then there's also an instrument that goes on the ships, and we just set it and dial a few knobs and press some buttons, and we get some very sensitive measurements.
Would this be something that I might want to ask my wife to give me on my birthday or
Well,
for Christmas?
you know, if you want to know about the internal structure of Nu'uanu, then this would be a great thing for you to ask your wife for. That's right.
All I would need is one, huh?
You would just need one, right? And they go for about $90K these days. So.
Okay, thank you. End of that conversation.
That's right. That's right.
So, and then we have a third photo or drawing graphic. Yeah, what's this one?
And this is related. This is Ashton, as a master's student, spent a whole summer at least, and some additional time taking this very expensive sensitive instrument, actually on his back, hiking around Kauai. And he produced a whole map of the gravity signal around the island of Kauai. And he used that data to invert for the density structure beneath Kauai. And what you are seeing is his inversions of the density. And so the two red dots you're looking at are the densest rock, which we think are the old, now dormant magmatic centers of Kauai to the right and Niihau to the left.
So let me just understand that if you have dense rock, then you have greater gravity there.
That's right. That's right. The Earth pulls down just a little bit harder when you're over the denser rock.
And how does this measuring device actually tell you whether it's dense rock and greater gravity?
Yeah, right. So it's a very simple system. It's a weight. It's on a spring. It's a very sensitive spring, and the longer the greater the gravity is, the longer the string stretches. The further that weight is pulled downward.
So you look for greater weight, and greater weight tells you that what's underneath is greater density.
Right. More mass.
More
Right?
mass.
Gravity is here because mass is attracted to mass. When there's more mass beneath you, you feel a greater pull of gravity. And so these are small variations. These are something like a millionth of the normal of a G, the pull that we normally feel. So these are very subtle variations in ways that we can remotely sense these density variations.
So you spoke of somebody who was helping you from the school. How does that work? I mean, you guys go out and do this research, and you have graduate students who help you, or undergraduates, or what? I mean, what kind of team arrangement is it when you go out and do this kind of research?
Right. So with our current Masters of Science program, our students are funded by and large through our extramural grants. So a lot of our research, all of our research basically is funded extramurally.
What does that mean? Where does it come from?
National Science Foundation, for example.
National federal programs.
That's right. That's right. And our students come in and they get an education on how to do basic research, and they're supported.
It's well worth their while to be involved in a kind of, because they learn a lot of stuff.
That's right. They're being trained as scientists.
But they're working for a degree at the time.
That's right.
So like a master's in geology, for example,
Right.
would be doing that.
So in many ways, they're apprentices. They're
Yeah.
doing the work that they will be when they graduate, and they're doing it under the advice of the scientists.
And they can go out and hike all over Kauai
They can.
in the process.
They can.
Not too bad.
That's right. Yep.
So how many of them are there when you have a given project like this? I mean, is the number of graduate students you have attached, directly proportionate to the amount of money in the project? I mean, how does that work? Or you create teams based on the need for the team?
Yeah, The number of students per project really depends on the scope of the project. In this last example of Kauai, this was one master's student mapping and doing the gravity of Kauai. In the cruise, the survey of the South Kauai swell, we had over a good handful of students working on various aspects of the project.
So when they do the project, say Kauai, is that going to be the subject of their thesis?
Yes.
So it all dovetails.
That's right.
And so if they pick that project to be involved in, or you pick them, it's an implicit agreement that they will be writing their masters on that same
For the most part. For a master's degree where it's primarily one sort of body of research that's written in one publication, right, so lots of times that's pretty well predefined by the advisor and they work on that. With a PhD, oftentimes as they mature and become more senior, then oftentimes they can better define what their research is. Mm-hmm. But it often starts with a more well-defined project and the students branching out from there.
Yeah. Okay.
But it's all supporting the research of the advisors. So it's a sort of a team effort.
They have classes too?
Oh yeah.
You guys both teach classes?
Yes.
What do you like better? I think I know the answer already.
You're asking Garrett or me?
Go ahead.
I actually love research, but I also really enjoy teaching too. When you were asking about when people started doing geology, when you teach, I teach mostly undergraduates, and the course I teach most regularly is the first course exclusively for our majors that kind of introduces them more fully to the history of the Earth. I love teaching that stuff because you sort of say, when did people start thinking about geology? Well, it goes back to mining. And in different cultures, it's very different, and it's great to have an opportunity to try to brush up on that stuff. It's part of your job.
Yeah.
So I really enjoy teaching and doing research.
Yeah.
And in many ways, they are complementary.
How about you, Garrett?
I agree. I guess as an assistant professor where the pressure was to publish and produce lots of research, teaching was sort of a thing I kind of had to do. But as I proceeded through the career path, I sort of thought of teaching as sort of taking my vitamins. It did complement my research in many ways. It really helped me learn a lot of the issues, go back to the basics, and that did affect my research. And at this point, it's a new challenge. Well, it's not necessarily a new challenge, but I'm taking it as a welcome challenge to become a better teacher and to make a bigger impact on my students and what they do afterwards. So
Better students, better
I wouldn't
researchers.
say I like one necessarily over the other. Research does consume a lot of time and I'm thankful for, but I know certainly the students that we produce is very important and enables us to do the other things that we like to do. That's right.
Okay, we're going to take a short break again. Garrett Apuzin-Ito, professor at SOWEST, and Greg Ravizza, associate professor at SOWEST. We're talking about, and we're going to get to this next time, introduction to the professional master's degree that's being developed in science called the MGEO. This is Think Tech Talks. I'm Jay Fidell. You're on the SOWEST Hour. We'll be right back. Aloha, I'm Jay Fidell of Think Tech. We have some news for you. In addition to our Think Tech TV show and our Asia in Review show on Olelo 54, as of January 1st, we're adding Community Matters to play also 2 hours a week. Check out thinktechhawaii.com for the specific times of each of these shows. We hope you enjoy all three. Mahalo, I'm Jay Fidell.
Aloha, I'm Maria Kashem of Think Tech Hawaii, and I want to tell you about our Think Tech talk shows. If you didn't know it, Think Tech streams video and audio for all of its shows live on the internet from 2 to 5 p.m. every weekday afternoon, and we replay them all night long on ustream.tv. Visit thinktechhawaii.com for our live stream and YouTube links. Raise your awareness on Think Tech. I'm Maria Kashem, and I'll see you there.
This is a hot show, actually. I'm really having a good time here. Think Tech Talks, the SOWEST Hour, the School of Ocean Earth Science and Technology. We're working our way up to an introduction to the professional master's degree that's being developed in science. It's called the MGEO, with Garrett Ito, professor, and Greg Ravizza, associate professor at SOWEST. And the question left hanging in the break, the break is really an interesting discussion always. Too bad you can't get to see that. Is, if I'm a student of French, studying French, can I walk across the campus and say hi and participate in a class on geology?
And the answer is certainly yes. I mean, certainly as a major in any other department, you have some basic requirements, and some of them involve science or natural sciences. So you can come over and take an introductory level geology course and learn a lot about geosciences.
And I think, I don't want to put words in Garrett's mouth, but I think if you were to ask any faculty member in our department, if they were in charge of the university, they would say every student at UH should probably take an introductory geology class or one of the introductory courses at SOS, because the earth we live on is a changing place, and it's where we get our resources from. It's what provides us sustenance and better understanding how that system is organized and how humans interact with it is tremendously important for any person who wants to consider themselves well-educated to have a good grasp on it. And the introductory courses we teach do a good job of introducing students to that.
Yeah, it's a matter of relating to the earth and the environment and not looking at your shoelaces all day.
Yeah.
I wanted to say, right, so geology is not just about rocks, right? So it's about the solid earth as well as the environment, the water, the air, and how they're interrelated. So geology, when we say geology, oftentimes we're speaking about earth science.
Yeah. Then you mentioned that a fellow in my condition, my delicate condition, I could come down and order the class, which
So I
is...
should say, you didn't get to the break, but when Jay dropped that question on us, I said, well, Jay, I hesitate to ask how old you are. I won't give the answer.
Thank you for that.
As someone who is ripe with wisdom and experience, senior citizens can come to UH and are free to audit any course they like with the instructor's consent. And it's a great program.
It's a great program.
And I've had some students come and take advantage of the opportunity, and I've really, really enjoyed having them in class.
And they have too. I mean, I know a couple of guys who have done this, and they just love it. And they make a whole life out of it. It's like their whole career they didn't have this exposure, and now all of a sudden they've turned curious again. And to be curious is to be young, so it works on both sides.
I had a man in my class who was retired and was actually a geology and geophysics major. So
Fabulous.
you can do it.
Okay, well now I want to turn at this point, with 13 minutes to go, I want to turn to our main subject, and that is the MGEO. And as they say in the French class, qu'est-ce que c'est que ça? What is that?
So the MGEO is our professional masters in geoscience, and it's a degree designed for applied geosciences. So, for example, the coursework, for example, emphasizes applied courses, and therefore it's for a student who is not necessarily interested in the basic research, but is more interested in working with industry or an agency in geoscience-related fields.
Okay. What do I have to study before prerequisites?
The prerequisites are basically what is required for our current MS degree. Mm-hmm. So you need a degree, a BA or BS in natural sciences, and it helps certainly if you have a lot of the prerequisites for the classes that we offer. You also have to take your GRE, your graduate entrance exam, and good grades help a lot.
Mm-hmm. Not everybody gets admitted.
That's right.
And examples of the types of students who might be interested in pursuing a degree like this could be someone who is now working on the islands with an undergraduate degree, perhaps in environmental science, biology, chemistry, physics, but has found their way into the geosciences or geotechnical fields. This might be assessing hazardous materials on sites or working on remediation, and they may want to pump up their skill set a little bit. And so even without specifically a geology degree, a good student like that could come in catch up on the introductory geology courses that they may need, and then pursue work at the master's level. And we have a great set of classes that basically impart upon the students the skill sets that you need to do both applied and academic work. So working with data, acquiring data, those types of skills, quantitatively analyzing it, doing some modeling as Garrett does, those are all skills that we use in academics and are, extensively used in the private sector geotechnical work, geoscience work.
So this is a program that's designed to prepare you for work in the private sector,
Yes.
essentially.
Yes.
And the private sector could mean industry or it could mean activism just as well.
Or
nonprofits or profits,
yes,
all the
yes,
same.
absolutely, absolutely.
So why are you putting this together? I'm sure that, establishing another program in any university is a certain amount of work. And maybe some paperwork and drudgery even.
Oh, yeah, sure.
And frustration and bureaucracy.
Garrett can speak to that.
You don't want to hear about that, believe me.
It was a very hard thing to swing for exactly all these reasons. Why do we need to do this? I think that there are perhaps two reasons, or two main reasons. One is over the course of many years, we were getting feedback from our alumni and from employers on the island that there is a need for this. And specifically, many of the consulting firms involved in environmental work and geotechnical work are eager to have a well-trained pool of people that they can hire from on the island. And the reason for that they have expressed in one of our recent meetings.
There haven't been enough people.
Well, they can hire from off-island, but it's often difficult to retain.
Yeah.
And so if people are from here, their families here, they understand what it is to live here, they are more likely to
The old story.
stay and be happy. Whereas if you bring someone in,
don't
they
know.
may have some vision of what it's like to live in Hawaii, but it may not be the same as they imagine once they arrive. And there's a investment in training and all these things that these firms need to make over and over again every time someone comes from the mainland and is not happy here.
Yeah.
So that's one reason, and then the second reason you're going to go into the sort of efficient utilization of resources.
Yeah, sure. So we basically can handle more students. Okay, so we have between 20 and 30 master's students in our Masters of Science degree program, and we can teach more students. But our enrollment,
Economies of scale kind of thing.
well,
You have the ability
our
to teach them.
courses are not full,
Right.
are at the graduate level, and that's our enrollment is in fact limited by the scientific research projects we have and the extramural grants that we have. So we have the capacity to take in perhaps twice as many students.
So you want to fill those seats.
That's right.
And if you offer these additional courses, additional career track really is what it is, you'll have people who would be interested and will fill the seats.
And
It's a
they're
great
becoming
idea.
skilled people to stay here and work on the island.
Yeah.
Yeah.
Well, and that's what I want to get into. I mean, it's really actually it's a win-win-win-win-win kind of thing, because at the end of the day, the community will have more scientists who can help, cross the Rubicon and help in the non-academic side of things, and presumably that will help the community. And then you'll have a larger body of graduates, a greater, what do you call it, distribution of the science.
Yep.
And so a greater presence through the graduates kind of thing.
Greater diversity of our students
Yeah.
to interact with.
Yeah,
Sure, you
yeah.
bet. I think.
So if I take this course, and by the way, I studied economics. It's a long way.
Yeah.
I did have a little French, but if I take this course, then and I finish successfully, get into the program, and then conclude the course, get the master's degree, is that enough for me, or do I need to have a PhD on top of it?
No, definitely not. I would say that in the earth sciences, a master's degree is considered the preferred working degree. And so
the
really,
PhD takes too long.
a PhD not only does it take a long time, but really, when you do a PhD, certainly in our program, you are being trained primarily to do basic research of conceiving an important question, a fundamental question, and then learning what you need to know in terms of skills to acquire that information, that new data, and then interpret it, really at a very fundamental research level. And that can take 5 to 6 years easily.
And it draws you away from the connection with the community.
Well, actually, so in industry, people with PhD do lead the research. Okay, they do the research. So in many ways, a master's degree opens up more more diversity of opportunities in many ways to someone going into industry. They can in many ways, at times they manage research scientists.
Sure.
And you're becoming extremely
Yeah.
specialized when you do a PhD. You know, one of my little rants about how specialized my work is, when you go into industry, you have no idea who's going to hire you.
So there's a greater flexibility. there.
Yeah, so you obtain a set of abilities that is more general, whereas when you do PhD work, it's much more common to specialize at a very high level, and there's no guarantee there will be a job for a lot of people who are very highly specialized. But if you are familiar with these broad issues of how the Earth works and how we acquire information about contaminants or the water cycle, that's broad general information that is marketable.
Well, sorry.
And you asked about whether, after going through the degree, whether you'd be prepared to jump right into the work. So one of the highlights of the degree is our students, in addition to taking courses, they're going to do work with a company or agency that they choose. So
At the
instead
same time.
Yes,
During-
instead of
during
doing
your
a
time-
master's thesis, their culminating experience is a work project, perhaps as an intern or already being an employee in the company. It's a project that they will see from start to finish. They'll do it with the company, they'll get experience with that type of work with the company, and they'll write up a report and do an oral presentation.
So they get a double whammy right there.
Sure.
And it's
then
great
maybe they
for-
get a job right after in the same company. you know?
That's a possibility.
And it's great for us as faculty because this has already begun to foster better interactions and exchange of information between our faculty and the working geoscientists, certainly here on Oahu. And most of the folks working here on Oahu are going off island to the neighbor islands for a variety of things too. So it's really improving our ability to interact with and understand the immediate local needs in the earth science, geoscience arena.
Well, it's that whole thing that Tom Apple talks about, extending out the university into the community, doing good works, including getting a job in the community, and expanding the university's presence and influence all through the community in a kind of synergistic relationship.
Yes.
And he's all into that, so that's great. This is happening. So what kind of company would I work for? What kind of, who is out there that wants me?
So one of the areas that are certainly relevant to Hawaii is environmental consulting. So this is, for example, contaminant detection and remediation. There's also water resources is a big area in Hawaii. So we have a number of people in our department who work on hydrology and hydrogeology. So understanding where water resources are, how contaminants may affect them, and how changes in climate, for example, might affect that. Another area is
Before you pass
Sure.
off from that, there is a thing happening now, I want to say Molokai, where they're going to do pumped hydro for energy storage. This is a big geological question about how you do that on a grand scale, on a scale big enough to contain all the energy that you need to, run the generators when there's no solar, for example.
So you're going to use solar to pump the water up to some big
Exactly.
storage area. I mean,
Right.
they're going to build a dam or something, or what are they?
You guys will have to answer
So
that.
there are tremendous environmental impacts associated with that kind of stuff. To make
Yeah.
another tangible example is Ali Al-Qadi, one of our colleagues in the geology department, had a PhD student who finished not too long ago, and he was specifically interested in arsenic. And so arsenic is common in many of the pesticides used during the heyday of cane farming. So now real estate developers, when they go into former cane land, need to survey for arsenic. And so Bill implemented Bill Cutler, who was the PhD student. He's now back in Colorado, but comes back and forth periodically. So he's in the environmental consulting business. So a developer would have to employ a consultant to come in and do an assessment and say, is this property contaminated? Or before I develop it, do I need to remediate? Do I need to remove some of the topsoil, or do I need to put some clay on top of it? Is it safe? And so these are the types of jobs, these are when we say consulting jobs, that's an example of the type of work people need to do.
What else? You had other things?
Geotechnical engineering. So when anything needs to be put into the ground, a building, built a road, There are various engineering aspects of that, and so many civil engineers get trained in that. But being in Hawaii, the rocks are in many ways unique or very different from
And you need
elsewhere.
a real geological
So
expert.
one of our feedback from our alumni is we need better people who are more trained in Hawaiian geology, for example. So an engineer, a civil engineer who is in that field, could get an MGEO and learn quite a lot about the structure of the Hawaiian rocks and the processes, for example, that might pertain to that sort of research.
But I know your real motivation.
Tell us what it is.
You
Tell
know,
me.
you know that these issues are becoming more pressing all the time. You know that environmental considerations are more pressing all the time. With climate change, you know, and the changes in the coastline,
Yep.
more pressing all the time. With storms, who knows what, water, right? You mentioned water. All these things are going to come into our lives
Yes.
big time in the next 10, 20 years, and we're going to need people to fix them and all that.
Certainly that is another arena where our graduates have currently found employment and we expect would be appropriate for MGEO people, is also in state jobs. You know, I mean, managing water resources, there's several entities within the state that are responsible for that, and you know, monitoring flow, water quality issues, those are all important things.
A great idea.
And so when we reached out to the community, we were not just with private sector people. There were also a number of scientists who work for the state in different capacities who came and gave us great input, really valuable input. And there's a real interplay there because the state officials are responsible for enforcing the laws, and the people out doing assessments and doing remediation must respond to the laws and the way they're being enforced. And so we're bringing these people together, and we, in fact, are learning ourselves sort of how these are implemented and what the skill sets are that people need.
Then
to
you can
work
adapt the
effectively.
program to make sure to satisfy them.
Absolutely. And I think that we as faculty will certainly learn a tremendous amount.
Great connection.
Yeah, I'm excited about it.
So when does it start?
It's happening, well, we're taking applications now. They're due the 15th, actually.
To the 15th,
Yeah.
2 days from now.
That's
I'm glad
pretty
we had
soon.
the show today.
That's right.
You guys.
Yeah, get your applications in soon.
But it's the sort of thing that will start slowly, certainly. I mean, if we were to have 50 people apply immediately, there's no way we could accommodate them because they need to be matched up with projects and that it will be tailored to their interests. And so it's something that will start small to maintain quality and grow over time.
Taylor. Is that a pun?
Could be, that's right. Brian Taylor, our dean, has been heavily involved in designing and sort of refining the project.
It has been tailored. It will continue to be tailored.
Okay, Garrett Ito, professor, and Greg Ravizza, associate professor at SOEST, at the Geology and Geophysics Department of SOEST. We're talking on the SOEST Hour. We're talking about this new master's degree in science, MGEO. Thank you very much, gentlemen.
Thank you, Jay.
Thanks a lot.
Thanks.
Been
We'll do
fun.
it again.
Yeah.
Good luck on the
Hope to.
program.
Thanks a lot. Thanks a
Thank
lot.
you.
Aloha.